There's an interesting subset of Prolog called Datalog. Datalog is the functor-free subset of Prolog, more precisely of pure Prolog. So this means Datalog is Prolog without compound terms and without impure predicates, such as input, output, cut, and so on. And therefore, a Datalog rule is like a Prolog rule with a few additional constraints. A Datalog rule has a head and a body. The head must not contain compound terms as arguments, and the body must not describe compound terms and must not use impure predicates. These are syntactic restrictions on Prolog programs, and we therefore say that Datalog is a syntactic subset of Prolog. And since Datalog is a subset of Prolog, every Datalog program is of course also a valid Prolog program, and therefore also a valid Prolog term. And a major benefit of this is that we can easily use Prolog to reason about Datalog programs. For instance, we can use Prolog to very precisely define what we mean with a Datalog rule. So let's do it. Let's define a predicate called Datalog rule, which shall hold for a rule if and only if rule is a Datalog rule. So let's think about it. When is the term rule a Datalog rule? Well, as just mentioned, rule must have a specific syntactic shape, namely this one. That is, it must be a compound term with principal functor colon dash and two arguments, the head and the body. And we can of course state this directly in the head of this clause. So instead of speaking about rule, we can say directly a Datalog rule is a term of this shape. Now, what must hold about head and body? Well, there must not be any compound terms in arguments. So starting with the head, if args are the arguments of head, then something must hold for each of these arguments. Namely, each argument must not be a compound term. Or in other words, each argument must either be a variable or an atomic term. Let's call this property var or atomic. And it must hold for all arguments of the head. Then what about body? Well, this is a bit more complex, so maybe we best introduce a dedicated predicate for it. Let's call it isBody. So isBody must hold for body. And with this predicate isBody, we describe what must hold for the body of a Datalog rule. And I said it's a bit more complex because body can be a compound term and can even have compound terms as arguments, because a body can contain conjunctions of goals. So the problematic default representation of Prolog rules carries over to Datalog rules. And therefore we must distinguish, are we talking about a conjunction or not? And unfortunately, we can't distinguish the cases symbolically. So let's first consider the case where body is not a conjunction. So body is not a term with principal functor comma and two arguments. Then what must hold for body? Well, as above, the arguments of such a body must be variables or atomic terms, but not compound terms. And such a syntactic element which is not a conjunction and also not a disjunction and so on, but only a predicate symbol and its arguments is also called an atomic formula. And if we want, we can again introduce a dedicated predicate for this, say atomic formula. And we can of course use it not only for body terms, but for all terms. So this is a specification of what we mean with an atomic formula. And now we can refer to this specification when defining what we mean with a rule body. If body is an atomic formula, then body is a valid rule body. And we notice, for example, that we can apply this concept also here when defining the head of a rule, because syntactically, the head of a Datalog rule must be an atomic formula, because no control constructs, such as conjunction and so on, must occur in the head. In contrast, conjunctions may occur in the body of a rule. So currently, our definition of what a body is too specific. So we must generalize our definition. And we do this, for example, by adding another clause, where we say that body may also be a conjunction of goals. And a conjunction A, B, which we read as A and B, is a valid body if A is a rule body and B is a rule body. So now we've defined the general shape of Datalog rules, functor-free Prolog clauses. In fact, our definition is too general at the moment, because we haven't constrained rule bodies enough. and I leave adding such restrictions as a challenge. I will add one restriction though, which is important for Datalog. And that restriction is every variable that occurs in the head also occurs in the body. That's a so-called safety condition because it prevents infinite set of solutions. And we can easily add it to our definition by adding this safety condition as a constraint. Namely, if these are the variables that occur in the head, then each of these variables must occur in the body, okay? So this is a useful starting point for a definition of what a valid Datalog rule looks like. It's a Prolog rule with certain additional restrictions. And I leave implementing these two predicates as an easy challenge. And a key attraction of such a Prolog-based specification is that it's executable. This means that we can actually use it to ask Prolog whether a term is a valid Datalog rule. For instance, we can ask, is the following a Datalog rule? Ancestor descendant of A and D if parent-child of A and D. Is this a valid Datalog rule? Well, that's a syntax error. Because we must use additional round brackets for the argument due to the priority of the operator :dash. And yes, that's a valid Datalog rule. So we can use our specification to test the validity of Datalog rules. And that's in fact a major attraction of Datalog. Because Datalog is a syntactic subset of Prolog, we can very easily reason about Datalog with Prolog. And for example, it's easy to state more constraints, such as about the principal functor we allow for atomic formulas. For instance, as mentioned, we should add more constraints here to exclude disjunctions and also other predicates that we don't want to allow in Datalog, such as IO, cut, and so on. And we can do this easily because Prolog lets us easily reason symbolically about terms and therefore about Datalog programs. So this is the syntax of Datalog programs. Datalog is the functor-free subset of pure Prolog. Then what about the semantics of Datalog? That is, what is the meaning of such programs? Well, the semantics can be defined in several different ways. For instance, if we denote with d of p the denotation of a predicate symbol p in a set of clauses A, then we could define this function in a model-theoretic way, yielding a model-theoretic semantics, where we define the meaning of a predicate symbol in terms of models of the clauses A. For instance, we could say d of p is a certain set, namely a set of tuples t1 to tn, for which it is the case that p of t1 to tn is a semantic consequence of the clauses A. So this defines the meaning of a Datalog predicate in terms of models. We mean all tuples of arguments t1 to tn that make the predicate hold in all models of A. Another way to define the meaning of a predicate is to give it a proof-theoretic semantics. This looks almost like the definition above, except that we replace semantic consequence by syntactic consequence. So now we no longer talk about models, but about proofs. And we now say we mean all tuples that are syntactically entailed by the clauses A. So all tuples for which we can derive a proof that they follow from A. And as a special case of proof-theoretic semantics, we can also give a Datalog program an operational semantics by specifying a concrete proof strategy, such as SLG resolution. And analogously, we can also consider a special case of model-theoretic semantics, called the fixed-point semantics. This defines an Aubron model as the least fixed point of a transformation T, which saturates the set of clauses with semantic consequences. So, from a logical perspective, these are two major ways to define the meaning of Datalog programs: model-theoretic semantics and proof-theoretic semantics. And both of them allow specializations by specifying concrete computation strategies. And these computation strategies are interesting, for example, for implementers of Datalog, whereas we, as users of Datalog, don't really care about how the consequences are derived. For instance, the concrete proof strategy doesn't matter to us as long as we get only correct results and all correct results. Because the actual result we are interested in is the logical consequences of a Datalog program. So we, as users of Datalog, want to focus on a clear description of what holds, and we expect the Datalog implementation to do everything it can to efficiently compute logical consequences. And we, above all, expect the system to be correct. And with suitable design choices of computation strategies, all these notions coincide for pure Prolog and therefore also for Datalog. This is very elegantly shown in a paper by Martin van Emden and Bob Kowalski. Now, let's consider an actual example of Datalog. Say we are reasoning about graphs, and we want to determine reachability in a graph. For instance, let's consider this sample graph. This is a directed graph with 4 vertices. And for example, from vertex A, we can reach C, but from vertex C, we cannot reach A, because there is no directed path to it. So let's first describe this graph in Datalog. And we don't even need rules for this, because it suffices that we directly represent the graph in a form we call an extensional database. Here we state in a very concrete way, for example, that there is an arc from A to B. Further, there's an arc from B to C, one from C to D, and one from D to B. So this is a graph with 4 vertices and 4 arcs, and that's all we need to know about this graph. These are also called facts, like in Prolog. So an extensional database is a collection of ground facts. And in addition, we can define Datalog rules. And these rules can refer to facts and also to other rules. For instance, in our case, we said that we want to reason about reachability in a graph. So let's introduce a relation called reachable. And this relation shall hold for a vertex from and a vertex to if we can reach to via a directed path that starts at from. So if we can go to from. So this should be the head of the rule. And as already mentioned, we use colon dash between head and body of a rule. This is like in Prolog because colon dash looks similar to an arrow from right to left. And we can read a rule as an implication. If the body holds, then the head holds. And now we only have to define when this shall hold. That's the interesting part, because now we need to state very precisely the conditions under which a vertex is reachable. Well, one case is obvious, right? If from is equal to 2, then 2 is of course reachable, right? That's because a vertex is trivially reachable from itself. But there's a problem here, because there's strictly speaking no guarantee that the predicate equals, which denotes syntactic equality of terms, is available in every Datalog implementation. Yes, it's a pure predicate, and a Datalog implementation may provide it, but it may also omit it. And one problem we have is that we also can't define equals within Datalog. That's different from Prolog, because in Prolog, if equals were not available as a standard predicate, then we could define it ourselves with a single fact. But in Datalog, we can't do this because that would violate the safety condition we mentioned, because such a fact would hold for an infinite set of terms. So what do we do now? Well, we could of course state, for example, that we can reach 2 if there is an arc from to 2. That's certainly correct. But it wouldn't entail the reflexivity we expect from this relation. So what we do instead is we say V is reachable from V if V is a vertex. That's the simplest case, and we can easily state it as a rule like this, where we assume that we have, as part of the extensional database, a predicate vertex defined as a set of facts. And I leave the definition of vertex for our example graph as a simple challenge. And there's another case, namely, suppose there's an arc from, but not necessarily directly to 2, but to some vertex next, and 2 is reachable from next. Then, obviously, 2 is also reachable from. So that's another rule that we can certainly state. And in fact, this completes our definition. Reachable holds if and only if the second argument is a vertex that is reachable from the first argument. And that's remarkable because reachability can't be defined in first-order logic, but it can be defined in Datalog, and therefore also in Prolog, because Prolog and Datalog only consider least or Brown models. So this is how we write Datalog programs, as facts and rules. And the facts are also called the extensional database, or EDB. And the intensional database, or IDB, is defined by the EDB instance and the Datalog rules. This is where the interesting part happens, because the IDB is generated deductively as logical consequences of the EDB and the rules. And that's why we also call it a deductive database. Because a Datalog system performs such logical deductions for us and computes the logical consequences of the rules. And this concept of logical consequence is very expressive. For instance, with Datalog rules, we can express the transitive closure of a relation, as we've just seen with reachability. That's something that relational algebra cannot express. So database languages based on relational algebra need custom extensions to express it. And these extensions are often quite hard to use and also error prone. Whereas in Datalog, as we've seen, transitive closures are easy and natural to define. Then with logical consequences, we could in fact even express the extensional database as a set of rules. Because we could simply use a predicate that's always true to say a fact always holds. And if true isn't available, then we can easily define it with a single fact. For instance, we could turn this fact into a rule like this, right? It would mean exactly the same thing, but now we no longer have any facts, but only Datalog rules. So the concept of logical consequence has the potential to simplify our considerations by eliminating the distinction between facts and rules. And on the other hand, it's often useful to discuss the EDB separately from the rules, because the number of facts is often very large and the facts can also change a lot over time, whereas rules often stay the same over time and can also be applied to different EDBs. And therefore, when discussing Datalog systems, we often distinguish between EDB and rules. Another thing naturally expressed as logical consequences are views. For instance, we can implement a projection of reachable where we are interested in vertices that are reachable at all. And we can express this as these are vertices that are reachable from any vertex. So we know that these are all vertices, but still, the point stands. We can express views as logical consequences of relations. And the concept of logical consequence is in fact all we need to express all known computations. And in fact, we get this easily with a syntactically small generalization of Datalog. Because if we allow functors and compound terms, then this extension of Datalog becomes Turing-complete and can express all computations via such rules. Because then it's essentially Prolog. So Datalog is also interesting because it's in a sense very close to being able to express every computation we could possibly want. And this could greatly help adoption of Datalog, because from Datalog it's only a small step towards Prolog, and therefore to arbitrary computations. And let's think about it. How will the next wave of interest in Prolog arrive? Well, it could come in many ways. It could, for example, be generated by governments, like in the 80s by the Japanese government and the 5th generation computer systems project. And governments are a natural environment for Prolog applications because governments often care about transparency and explainability of decisions, and also about encoding law as code, so that laws can be more easily executed and reasoned about. It could also come from platform providers, such as cloud services, or also from software infrastructure projects, such as package managers, where Prolog could be used as a configuration language or as a specification language for dependency management, for example. Database vendors are of course also a possible source. For instance, SAP, Oracle and so on could one day say, well, what we have done so far is pretty good. And now let's build something even better. So let's build a database and query language based on Prolog. And it may also come from other directions, such as Prolog as a foundation of computer game engines, common apps, or as a logistics engine for large companies and so on. And our immediate goal is to steer such initiatives towards actual Prolog syntax. Because new projects have a tendency to build their own syntactic dialects, and they often don't immediately see the consequences. This, in fact, also sometimes happens with Datalog. And there are several systems that call themselves Datalog, but actually use their own custom syntax, which is not Datalog. Now, one could of course say, well, but it's just syntax, right? But that, in a sense, downplays the importance of syntax. Personally, I think syntax matters, especially in the context of Prolog, because Prolog syntax is critical for easy meta-interpretation, program slicing, and so on. One could of course also ask, well, if it's only syntax, then why even care about it at all? And more directly, why then even choose a custom syntax in the first place? Because if syntax doesn't matter to you, then you may just as well use standard Prolog syntax. And personally, I would recommend that you call your system Datalog if and only if it supports Datalog syntax. For instance, if we search for Datalog and go to the Wikipedia page, then we immediately see it here. Syntactically, Datalog is a subset of Prolog. So every Datalog program consists of Prolog terms, such as here and here. A Datalog system must support this syntax, and it must support it verbatim. So please avoid strange ad hoc modifications, such as a different syntax for variables, a different syntax for rules, and so on. And here's an example query, which is also a valid Prolog term. There's also a bit of information on evaluation of Datalog. There are different execution strategies, just as for Prolog. And here we find a list of implementations of Datalog. Not all of them are true Datalog systems, but some of them are true Datalog systems. And for learning Datalog, I highly recommend DES, the Datalog educational system. This runs on several Prolog systems, and it also supports a number of extensions of Datalog. So Datalog means that your system uses a subset of Prolog syntax. And for clarity, it's best to avoid calling any system a variant of Datalog, because you're either using Datalog syntax or not. But it's true that there are fragments of Datalog, such as Datalog without rules, only facts, or Datalog without recursion and so on, and extensions of Datalog, such as Datalog with compound terms, or with optional type systems and so on. So such a terminology is of course valid. You can say you implement a fragment of Datalog or an extension of Datalog. And for instance, the Mangle project uses exactly this terminology, because here in the README, it says right from the start, Mangle is an extension of Datalog. So this means that Datalog is supported as a subset, or as it says here, a fragment of the language. So this implementation and documentation is really exemplary, because from this it's clear that actual Datalog syntax is supported. And Mangle goes beyond this subset and provides extensions. And ideally, such extensions also use valid Prolog syntax. And they may go beyond Prolog in terms of semantics, but ideally at least, such programs are still valid Prolog terms. For instance, this is a valid Datalog program and therefore also a valid Prolog program, whereas in this example, we have a valid Prolog term up to here, but this is no longer valid Prolog syntax, because that's not a valid Prolog token. So unfortunately, such programs can't be read and reasoned about as Prolog terms. So making extensions also valid Prolog syntax would be even better. And in other cases, better say, for example, that your system is inspired by Datalog. And another tip for marketing a Datalog system: make the marketing at least internally consistent. What do I mean by that? Well, let's consider an internally inconsistent marketing strategy. First, we provide a Datalog system, but it's actually not Datalog. So this is already internally inconsistent, in the sense that the statements contradict each other. You either provide Datalog or you don't. They can't both be true. Now, the marketing material may try to explain this. Yes, we use our own syntax, but syntax is not important anyways. Okay, then why are you using your own syntax if it's not really important anyways? So again, either syntax is important, then use Datalog syntax, or it's not important. Then why don't you use Datalog syntax? And also, if you use your own syntax, then it's not Datalog. So the marketing I've seen by some systems then states more or less the semantics are the only thing that count. And that may indeed be the case or not, but you can't then consistently also claim that the semantics are completely different from Prolog. Because if you care about semantics, then you know that the semantics of Datalog and Prolog are the same, or rather can be made the same with suitable design choices, such as choosing a complete search strategy in both cases. So many of these statements contradict each other already, and that makes the marketing strategy internally inconsistent. Now let's think about it. What is a truly unique attraction of Datalog? Why is it especially compelling, more compelling than SQL and so on? Well, as mentioned, from Datalog, it's only a small step towards Prolog. And I think a good marketing strategy for Datalog emphasizes this. And a good Datalog implementation retains a path towards full Prolog. That's a truly unique selling point of a Datalog system, that you can say, okay, we give you this cool database and query language, and in the future, we can extend it with the ability to perform all computations in a way that blends in completely naturally. For instance, let's consider again our definition of reachable. This was the Datalog program, the facts and the rules, with vertex left as a simple challenge. And it's of course also valid Prolog code. And we can therefore run it with a Prolog system. For instance, let's try it with Scryer Prolog and ask, for example, the most general query. Which solutions are there at all? And in response, we get answers from the system. In this case, a concrete solution. And on backtracking, Prolog reports more solutions until we ask it to stop. So that looks good. We can use Prolog to compute solutions. But we still have a small problem, because let's consider termination of this query and let's ask, does the query terminate? Well, no, the query doesn't terminate, it loops. Because for a terminating query, we expect to get false as answer in this case. So why does this happen? Well, our graph has a directed cycle, BCD, BCD and so on. And therefore, even this much more specific query, is B reachable from B, already doesn't terminate. So we observe the default execution strategy of Prolog yields non-termination in this case. And we also recall a Prolog program is an executable specification. And we can interpret it with any execution strategy we want. And different execution strategies have different termination and also performance characteristics. For instance, the query terminates if we use SLG resolution to interpret the program. This is also called tabling. And many Prolog implementations provide it. For example, in Scryer Prolog, we can easily enable tabling with library tabling. We load the library with a use module directive and then use a table directive to interpret reachable with SLG resolution. And now the query terminates. So we can readily run Prolog code with different execution strategies. And we can generalize this query and ask which vertices Y are reachable from B. And we get B itself, of course, C, D, and no others. And the ability to run Prolog code with different execution strategies is a major attraction of Prolog. A Prolog system may provide them for us, such as in the case above, and if not, then we can easily implement them ourselves by writing meta interpreters, which is very easy as long as we use Prolog syntax, because then Prolog programs can be easily read as Prolog terms, whereas syntactic variants, of course, lack this benefit. So it's good to keep to Prolog syntax and also to keep to the pure monotonic core of Prolog, where we can apply different execution strategies. And speaking about execution of Prolog and Datalog, what do we actually want from it? Well, our goal is of course to efficiently derive semantic consequences. And as just mentioned, a major attraction is that we can do this in different ways. As long as a few properties we care about are preserved, the execution strategy doesn't matter to us. And the most important property of an evaluation strategy is called soundness. This means that only semantic consequences are derived. So if it's derived, then it's a semantic consequence of the program. And the converse is called completeness. If it's a semantic consequence, then it's derived. For instance, the default execution strategy of Prolog doesn't have this property, but we can run Prolog code in such a way that we get it. And for Datalog, we should insist on this property. And as a distant third, we care about efficiency, such as efficiency in space, time, or that we can try different strategies in parallel and so on. Efficiency is less important in the sense that it doesn't help us if the other two properties are violated. But it's nice to have. And I know that efficiency is often a major selling point. And that's also why Prolog's default execution strategy is SLD resolution. Because it's often very efficient, at the cost of completeness. And as we've seen, it may not even terminate, even if there are only finitely many solutions. And efficiency ought to be a very distant concern if an execution strategy can't even guarantee termination in such cases. And even if it does terminate, SLD resolution can be extremely inefficient. For instance, it may take exponential time to derive polynomial many consequences. And as an example, let's consider a directed graph where the vertices are connected like this and also like this, okay? So this is the pattern of connections between vertices. And we only consider finite graphs of this shape. So there's a finite number of vertices. Then the number of paths increases exponentially in the number of vertices. And SLD resolution must traverse every path. So if we ask Prolog which vertices are reachable, then with the default strategy, it will take exponential time. Even though the number of solutions only grows quadratically in the number of vertices. So SLD resolution has a major drawback in general, even when it terminates, because it may revisit branches of the search tree redundantly, as in this case, where it reports vertices redundantly encountered over different paths in the graph. So what can we do better, or at least differently? Well, we already know one way to guarantee termination if there are finitely many solutions, namely by using tabling. So SLG resolution instead of SLD resolution. This is often a good strategy, but quite hard to implement. So not even all Prolog systems have it. And even though it helps to improve termination properties, it also has exponential overhead in the worst case, as in our example graph. And both of these are instances of what is called top-down strategies, because they start from the posted query and then proceed with the predicates used in the query. That's in contrast to bottom-up strategies. They start from the program and work their way up, in a sense, to the query. And we know that we can always find a model of the program by instantiating all arguments of all relations with all atoms that occur in the program. That's certain to yield a model, because then all implications hold. But that's of course not the intended semantics of Datalog. What we need is, as already mentioned, a least model, namely the least or Brown model. That's what we mean with the Datalog program. We're not interested in a model where all relations hold for everything, but rather the smallest such model that makes all implications true. And this suggests an extremely naive strategy, which we could call generate and test. Because we could simply generate increasingly larger subsets of such instantiations and check whether they are a model. And then simply take the first and therefore smallest model we find in this way. That would work, but it has a major drawback because the number of subsets is exponential in the size of the extensional database. And that's especially bad because the EDB can be quite large. And fortunately, we can do a lot better because the fixed point semantics gives rise to an evaluation strategy that's still somewhat naive, but much more efficient. It can be defined in terms of a transformation TP called the immediate consequence operator, which derives all consequences it can find for each rule until a fixed point is reached. This runs in polynomial time in the size of the EDB. That's because each application of TP can be performed in polynomial time, and there can be at most polynomially many solutions if we consider the rules fixed. That's because in every solution, each argument of a predicate must be one of the atoms that occur in the program. And at the very most, the number of solutions for each predicate is the number of atoms in the program raised to a fixed power, namely the number of arguments in the predicate. And therefore we reach a fixed point in polynomially many iterations. So that always terminates, and it's asymptotically a major improvement over SLD and SLG resolution. And even further refinements and improvements are possible. For instance, from one iteration to the next, we could intelligently focus on newly derived consequences to avoid redoing earlier steps. And in fairness, bottom-up strategies also have a major drawback because they may compute logical consequences that are not even needed to answer the query. And therefore, a top-down strategy may often be faster, even if it has asymptotically worse worst-case performance. And there are also techniques that try to combine the advantages of both approaches. For instance, the magic sets transformation rewrites the rules by taking the query into account so that a bottom-up strategy computes only those consequences that are actually needed. And that's great if it works, but sometimes this only yields overhead and no reduction. So that's no guarantee for greater performance. But a Datalog system is of course free to use any of these strategies and can even apply many of them in parallel. And for implementers, all these strategies are definitely worth studying. Now, let's think about it. How hard is it to evaluate a Datalog program? Well, as already mentioned, if we regard the rules as fixed, then all semantic consequences can be derived in polynomial time, and therefore also space in the size of the EDP. And that's the most relevant factor in practice, because there's often only a small number of rules, but the EDP can be huge. So that's good news. And this is called the data complexity of Datalog, because the EDP tends to store the actual data. And one can show that this data complexity of Datalog is P-complete. That is, if the rules are regarded as fixed, then evaluating a Datalog program is, in addition to being in the complexity class P, in general also as hard as the hardest problem in P. And one could regard it as bad news and say Datalog can be very hard to evaluate. And that's true. But on the other hand, this means that Datalog is quite expressive. It means that it can express, even by varying only the EDP, all problems in P with at most polynomial overhead in time and therefore space. And I will show this by first proving that satisfiability of propositional Horn clauses is P-complete. This is because if we are given an arbitrary Turing machine and the question, does this Turing machine accept a given input I in a polynomial number of steps in the size of the input and for a fixed polynomial, then we can express this question in terms of satisfiability of such Horn clauses under log space reduction and therefore with polynomial time overhead. And I now sketch the clauses. First, I use a set of propositional atoms CC with a subscript, and this denotes the cell content at a particular position of the tape and at a particular step of the Turing machine. And the subscript indicates the symbol that appears in that position. And I denote in brackets the time tau and the position pi. So I use this notation to say, in this case, the cell content at time tau plus 1 and tape position pi is alpha prime. And I use this notation abstractly, because what I actually indicate here is a single atomic proposition. Because we are using here only propositional logic. So only constant symbols and variables that can be true or false. For instance, this could denote a concrete constant symbol, such as this one, without any arguments, and where we only need logarithmic space for each number. Whereas I now use this index and subscript notation because I need such atomic propositions for all symbols and all positions and all points in time. And this, for example, shall be true if, and now we express the given Turing machine in terms of such Horn clauses as implications. For instance, we can say this shall be true if the state of the machine at time tau is S and the cell content at time tau and position pi is alpha and the workhead position at time tau is pi. So these rules describe relations between cell contents at different times and positions, depending on how the Turing machine is defined. And analogously for the states of the machine, the state at time tau plus 1 shall be S prime if the state at time tau is S, the cell content at time tau and position pi is alpha, and the workhead position at time tau is pi. And again, we use such rules for all states and so on. And in this way, we can model the entire Turing machine. And I leave a few remaining clauses as a challenge. For instance, clauses that define how the workhead moves, either left or right. Inertia rules that say that unaffected cells stay unchanged. And initialization facts that specify the initial tape content. And importantly, we state that except shall hold if the Turing machine is in state S at some point tau, where tau ranges over all times from 0 to the polynomial upper bound that we are interested in, as for the other rules, and we state such rules for each holding state S. And now we've set up the clauses so that the propositional formula except is entailed if and only if the Turing machine accepts the input in the given polynomial number of steps. So, for any Turing machine and polynomial time bound you give me, I can construct propositional Horn clauses that are satisfiable if and only if the Turing machine accepts the input in that time. So this shows that satisfiability of propositional Horn clauses, called Horn-SAT, is P hard, because it's at least as hard as the hardest problem in P. Because with such a reduction, we can use it to model every decision algorithm that runs in polynomial time. And moreover, Horn-SAT is itself in P. In fact, it's even decidable in linear time, which is as fast as we can ever hope for, because at the very least, we must read in the clauses. Well, in linear time on a RAM machine, not on a Turing machine. So, does this now mean that we can solve all problems from P in linear time? No, of course not, because the reduction is not free. It incurs overhead in space and time. But, as mentioned, it takes at most polynomial time and therefore space. And taken together, this means that Horn-SAT is P-complete, because it's in P and it's P hard. And as an aside, even a severely restricted version of Horn-SAT is P-complete because we can express a Turing machine with clauses that have at most 2 atoms in the body. For instance, we can factor out these parts into their own rule that only has 2 atoms in the body. And therefore, even propositional logic programming that allows only 2 atoms in clause bodies is P-complete. And now to the complexity of Datalog. Datalog can express a meta-interpreter for all propositional logic programs with at most k atoms in clause bodies. And it works like this. First, we store each propositional rule as an EDB relation where we relate the body to the head in arguments of the relation. All arguments are propositional atoms, so this works. And then for each arity of this relation, we define a fixed program, namely a meta-interpreter for P. We say t of x0 shall hold if t of x1 holds and so on, and t of xi holds. And these variables are the arguments of our EDB relation. So we use one such rule, a fixed rule, for each arity. And intuitively, we've now defined t of x to mean the atom x is true. And the rule states the condition that makes this hold. If x1 is true and x2 is true and so on, and xi is true, and these truth values ought to entail x0, then x0 is true. So in effect, we've now delegated the satisfiability check to Datalog. And we have A is a semantic consequence of the original program P if and only if T of A is a semantic consequence of the meta interpreter applied to the extensional database that encodes P. And that completes the proof. The data complexity of Datalog is P-complete. Because we can express under log space reduction every polynomial time algorithm as an extensional database that represents propositional Horn clauses and run the algorithm with a meta interpreter that can be expressed with a fixed set of rules. And we also know that we can evaluate Datalog in polynomial time in the size of the EDB. And there are shorter proofs to arrive at this completeness result, but this particular proof has a few nice properties. First, it in a sense leaves no doubt about the power of Datalog, because it works directly with Turing machines. Second, it shows that we can encode algorithms as data and interpret the data with Datalog rules. And this ability to interpret data and also programs is also a major attraction of Prolog. And here with Datalog, we already get a glimpse of this power. Because for any polynomial time algorithm you give me, I can encode it as a propositional logic program, store that program in a Datalog database, and then invoke a fixed meta interpreter to run the algorithm. And if you're, for example, a cloud provider that provides Datalog, then this also means that users of your platform can run all polynomial time algorithms on your platform by generating a database that encodes them. Because in Datalog and also in Prolog, code and data are very closely related. And that could be interesting for marketing purposes, because you then don't only provide a database platform, but also a computational platform. And that was just the data complexity, while leaving the rules fixed. And we get even more power if we allow changes in the rules. And the associated complexity is called program complexity, and also expression complexity and query complexity. Intuitively, the program complexity is higher than P, because the set of solutions can grow exponentially in the size of the program. For instance, if we have these two facts, so that's our EDB, and we ask for solutions, then we get two solutions, A and B. And if you turn this into a conjunction and add a single variable, then we get already 4 solutions. So by adding a variable, we've doubled the number of solutions. And with another variable, we doubled the solutions again. And this, of course, carries over to programs, because we can think of a query with a conjunction as querying a predicate where that conjunction occurs in the body. And indeed, one can show that the program complexity of Datalog is EXPTIME-complete. So a program can be evaluated in exponential time, and Datalog is also complete for this complexity class. It can express, with polynomial time reductions, all problems from EXPTIME. And I will show this again by reducing Turing machines to Datalog. And this time I'm considering all problems from EXPTIME. So all decision problems that can be solved by a Turing machine that holds in a number of steps that's at most exponential in the size of the input. And this time I will not use the EDB together with a fixed meta interpreter. I will instead encode the machine as Datalog rules, because we are now considering program complexity. And that means that we are allowed to change the rules. And we already know how we can do this, right? Because we can simply use propositional clauses as before, and they are already valid Datalog rules. But creating such propositional clauses as before would now require exponentially many, because we need rules for every point in time. And we said that the running time can now be exponential in the size of the input. So that would not be a polynomial time reduction. So instead of propositional formulas, we shall now use predicates to denote the cell content, the work at position, and the state of the machine at specific times. And we represent time points and tape positions as tuples over our universe 0 and 1. So we can think of time points and positions as numbers represented in binary notation, and therefore they incur only logarithmic overhead. And we define a linear order, less than or equal to, on these tuples. We say 0 is the first element and 1 is the last element of unary tuples. And the successor of 0 is 1, again for unary tuples. And for higher arities, we define these relations inductively. First, last, and successor, with higher arities. And I use vector notation to mean multiple arguments of these predicates. So this translation depends on being able to use arbitrarily high arity of predicates. And now we have an exponential number of tuples available for reasoning, even though we only used a logarithmic number of clauses. Linear in M, the length of the tuples, and the number of arguments. That's the advantage of being able to use Datalog rules, because as mentioned, they can express an exponential number of solutions, whereas EDP relations can only add polynomial elementi. And we can now refer to these tuples and express, for example, the cell content at the next point in time, x prime, and at position y shall be alpha prime if the state at time x is s, the cell content at time x and position y is alpha, the work at position at time x is y, and x prime is the successor of x. So we are using the defined successor predicate to reason about increasing points in time. And with this representation, we can cover an exponential number of steps. And the other rules are analogous. So in total, this means that we are able to use Datalog to solve every problem from the complexity class EXPTIME. And the program complexity is EXPTIME-complete even if no constants occur in the program, because the only constants we use in this program are 0 and 1. And these only occur in facts. And therefore we can move them to the EDP, leaving no constants in the rules. And the combined complexity, that is program and data complexity, is also EXPTIME-complete. Because the ability to add facts doesn't increase the program complexity, because we may just as well regard the facts as rules too. So the program complexity dominates the combined complexity. Now, what can we actually express with Datalog? First, it's clear that Datalog is a great database and query language. We can express databases as facts and rules, and even queries that relational algebra cannot express, notably transitive closures. And yes, SQL, for example, does support them, but they are far easier to write in Datalog. And also, Datalog is a programming language, not a Turing-complete one, but nevertheless a programming language, because as we've seen, it can express under log space reductions all problems in EXPTIME, therefore all problems in P-space, therefore all problems in NP, and therefore all problems in P. That's far, far more expressive than many of us ever need in practice. For instance, how many of us even know an EXPTIME-complete problem? Well, many of us do, right? Datalog is an example. But what about other than Datalog? Well, I, for example, had to look it up. For instance, evaluating a position in generalized chess and Go under certain rules is EXPTIME-complete. That's because these games, at least in some variants, can last for a number of moves that's exponential in the size of the board. Then what about P-space complete problems? Sokoban is a well-known example. Have you ever encountered this problem in practice, for example at work? Well, maybe, but many of us probably haven't. On the other hand, many of us have already encountered and even tried to solve NP-complete problems. And even more of us have likely tackled problems in P. And P is a huge complexity class, containing all decision problems that can be solved in polynomial time. And there is really many of them. And in practice, we tend to encounter only a tiny fraction of polynomial time algorithms, because for larger amounts of data, even quadratic algorithms are already intractable. So in practice, for larger n, quadratic time tends to be an upper bound for usable algorithms. That's well within what Datalog can express. And one of the few things known about these subset relations is that EXPTIME is larger than P by the time hierarchy theorem. And this means that Datalog can express more algorithms than many of us will ever need in practice. So we know that we can use Datalog to express and solve all EXPTIME problems with our reduction from Turing machines. And this is certainly interesting from a theoretical perspective because it shows the expressiveness of Datalog. But in practice, we are not so much interested in such reductions, but rather we want to answer concrete questions about given databases. So we don't want to transform or reduce anything, but rather write Datalog programs that can answer the questions we are interested in about any database that arises. And we know that for a fixed program, we can derive all logical consequences of a database in polynomial time in the size of the database. And we also know that we can express at least one p-hard query. And therefore, it's natural to ask, can we use Datalog to determine all database properties that are evaluable in polynomial time? For instance, can we write a fixed Datalog program that determines for each input database whether it is a connected graph? And the answer is no. That's because Datalog is closed under homomorphisms. And in particular, taking the subset relation as homomorphism, Datalog is monotonic. This means, for example, that if we add more facts, then everything that was previously the case remains the case. So adding more facts cannot invalidate derived logical consequences. And therefore, there are programs that cannot be written in Datalog, even for properties that can be evaluated in polytime. For instance, parity, that is determining whether the number of elements in the database is even, cannot be expressed as a fixed Datalog program, even though that's a decision problem from P. So we know that we can, in a sense, express it in Datalog, but not as a fixed program that decides this property for any given database. That's because parity is not a monotonic property, because adding a fact can destroy this property. Or as another example, connectivity, that is the graph connected, is not a monotonic property, because adding a fact may destroy the property. And therefore, there's no fixed Datalog program that correctly determines these properties for all databases. And as an aside, this is an example of an inexistence result. No such Datalog program exists. And I mention this because I've sometimes encountered the misconception that we cannot show inexistence of anything. But we can, and this is an example. And we can add extensions to Datalog to make it more expressive. For instance, let's consider semi-positive Datalog, where we allow negated EDB relations. So we can negate facts, but not rules. And that's a quite conservative extension, because we can easily simulate negated facts by adding additional facts as a new relation that holds for the negation of the given facts. So if we simply represent the database a bit differently. That's semi-positive Datalog, a very slight generalization of Datalog. And let's add one further extension, a total order on the domain elements, which we can obtain with 3 built-in predicates, first giving us the first element, last for the last element, and the successor relation. So we assume that we have these predicates available for each database. And that's again a quite conservative extension, because if a Datalog implementation does not provide these relations, then we can easily define them ourselves for any given database. And with these 2 small extensions of Datalog, we get a quite remarkable result from descriptive complexity theory, namely semi-positive Datalog on ordered databases captures P. This means that Datalog with these 2 extensions lets us evaluate precisely those database queries that are evaluable in polynomial time. So for every polytime question we have about any database, we can write a fixed Datalog program that answers this question for any given database. For instance, let's consider the mentioned question of whether a graph is connected. And we define connectedness inductively. We say the first node is connected. So here we are already using the total order on atoms. And further, if X is a connected node and Y is the successor of X and Y is reachable from X, then Y is connected. So here we are again using the order and also the relation reachable, which we've defined above. And for connectedness, let's say that we are reasoning about undirected graphs, or roughly equivalently about directed graphs, where for each arc y to x, we also have an arc x to y. And finally, we say the entire graph is connected if the last node x is connected. So this is one way to express connectedness of a graph in Datalog extended with a total order, something that cannot be expressed in plain Datalog. And personally, I think that's a quite remarkable property. The complexity class P, which is huge, is precisely characterized by such a simple formalism. It's exactly the set of problems we can decide with semi-positive Datalog on ordered databases. Now, let's sketch a proof of this. And we make a few simplifying assumptions. First, let's assume that the input database uses only a single binary relation, G with 2 arguments, and it represents a graph. And the nodes of the graph are integers. And we compute a Boolean yes or no predicate in less than n to the kth power steps. So we have to solve a decision problem from P on graphs. And we solve this once again by encoding a Turing machine that solves the problem. And again, we have to find a way to encode the points in time and the positions on the tape. And this time it must be a fixed Datalog program that solves the problem for any given database. And the main idea is again to use tuples to represent times and positions. And this time we can use the given total order on domain elements via first, successor and last. That's similar to what we had previously, except that this time we use the built-in versions of these relations and don't define them ourselves. So in this way we can again describe a Turing machine. And as initial tape content, we write the adjacency matrix of the given graph on the tape. We say the tape content at time 0 shall be 1 at the matrix position x and y if there is an arc from x to y. And it's 0 if there is no arc from x to y. So here is the only place we are making use of negation, but only for facts. That's why we need semi-positive Datalog. So that's the initial tape content and the remaining rules are straightforward. So to verify the property, we write the graph on the tape and then run the Turing machine expressed as Datalog rules. And I leave generalizing this proof to other cases as a challenge. And a few related results. First, no weaker language captures P. In other words, to capture P, a formalism must be at least as expressive as semi-positive Datalog on ordered databases. And without these extensions, the situation is less clear. For instance, omitting negation does not yield a language closed under homomorphisms. We know this because no negation is used in this example, and we know that connectivity is not monotonic, therefore not closed under homomorphisms. Then, what about queries that are evaluable in P and closed under homomorphisms? Well, one can show that plain Datalog does not capture them, and Datalog with successor ordering does not capture them either. So the situation is less clear without these extensions. And the general point stands, of course. We can add extensions to Datalog to increase its expressiveness. And usually extensions come at a price. And the price is often at least simplicity, because the use of extensions complicates the language, makes it harder to teach and learn, may make it harder to interpret, may limit the applicable execution strategies and so on. And just as for Prolog, extensions may also cost efficiency, because certain optimizations may no longer work or require subtle analysis and transformations. So there's often a trade-off involved. But still, many extensions are so useful that they are common in Datalog systems, even if they add complexity. For instance, let's consider negation in a bit more detail. Why would we need such an extension? Well, horn clauses let us state what holds, but not what doesn't hold. Nevertheless, we can infer that something is not the case if we interpret Datalog programs under the closed world assumption. Under this interpretation, we equate truth with provability. We regard as true only what we can prove, that is, only logical consequences. For instance, if we consider our graph example from earlier, then what we meant here is there are these arcs in the graph and no other arcs. And if we ask Datalog, are there any other arcs, then we expect it to say no. And not, for example, that it doesn't know, or that there could be other arcs too. And the closed world assumption is a common, but not the only way to interpret logic programs. And we could use other interpretations too, if they make more sense for our use case. And we've already encountered negation, because we've seen it in semi-positive Datalog, where we can negate EDB relations, so only facts. And in some situations, we need more expressive power. For instance, Datalog can express all operators from a relational algebra except set difference. So we can use Datalog to express projection, selection, renaming, set union, and Cartesian product, but not set difference. And if we allow negation, then we can express set difference too. And in fact, one can show that Datalog with negation, but without recursion, has exactly the same expressive power as relational algebra. Because each of the operators can be easily mapped to Datalog constructs and vice versa. And if you also allow recursion, then Datalog is of course far more expressive. So let's now try to extend negation to arbitrary relations. So we consider an extension of Datalog called Datalog with negation, where we allow negated atoms in rule bodies, but not in heads. So what is the meaning of such programs? Or rather, what shall be the meaning of such programs? Because the language should suit our needs. So we better give it a meaning that's useful to us. For example, suppose we define x is good if it's not bad. Then what are the consequences of this definition if we interpret negation as failure to derive something? Well, for instance, one consequence is that soup is good, right? Because there's nothing here that says that soup is bad. So bad of soup cannot be derived, and therefore the negation is true, if we take negation to mean that something cannot be derived. Similarly, bread is good under this interpretation, Prolog is good, and so on. And one major issue here is that under this interpretation, good holds for an infinite set of atoms. And one way to avoid this is to use a safety condition, where we say, for example, each variable that appears in a negated goal must also appear in a non-negated goal. This is another example of a safety condition like we had earlier, where we said every variable that appears in the head of a rule must also appear in the body. And let's consider a program where we don't have this issue. Say soup is good if soup isn't bad, okay? And now we face another major issue, because the program no longer has a unique least Approach model, but in fact two minimal Approach models. Because let's consider the cases. In every model, bad of soup must either hold or not. So suppose it holds. Then if soup is bad, we can interpret good of soup as false and obtain a minimal model. So soup is bad is a minimal model of the program. And second, suppose bad of soup is not the case. Then for the implication to hold, good of soup must be true. And so soup is good is also a minimal model of the program. So we now have a program with two minimal models, and which should we choose? Is soup now good or bad? Both situations are minimal models. And further, under the closed world assumption, we derive, if we ask, is soup bad? No, that's not the case, because there's nothing in the program that lets us derive this. So by the closed world assumption, we have it's not the case that soup is bad. However, there's also nothing in the program that says that soup is not bad. So we also cannot derive that soup is good. And therefore, under the closed world assumption, we also derive that soup is not good. So this means that we derive consequences that are not consistent with either of the above minimal models. And one way to solve these issues is called the stratified evaluation of Datalog with negation. This lets us distinguish a minimal Abram model in a very intuitive way, and it works only on stratified programs. A Datalog program is stratified if its predicates can be partitioned into strata, layers, in such a way that in each stratum, all predicates use only predicates from the same or lower strata and negate only predicates from lower strata. And such a partitioning is called a stratification. And the good news is that it's easy to determine whether a program admits a stratification, namely if and only if the precedence graph has no directed cycles with a negative edge, and you can find out more in the literature. And of course, the exact same test can be applied to Prolog programs. Everything we say about Datalog also holds for all Prolog programs of this subset. And for all programs that satisfy this condition, we can apply the stratified evaluation. This means that we can process the layers incrementally and apply the closed world assumption locally in each layer. And a key benefit is that this yields a unique model called the perfect model, which is independent of the chosen stratification. So that's one way to define a unique model for stratified Datalog programs with negation. And there are also other ways. And all these extensions we've now considered, negation, first, successor, and last, are examples for extending Datalog by adding built-in predicates, also called built-ins. All these extensions fit seamlessly into Datalog because they are simply predicates with the difference that they are not defined by us, but provided by the Datalog implementation. And when we implement the Datalog system, we can of course add further built-ins. For instance, an implementation could provide equals for syntactic equality of terms, or diff for disequality of terms, or arithmetic relations, such as arithmetic equality and inequalities. And as for all extensions, if we add them, then we gain something, and we may also have to pay a price. For instance, supporting a built-in may require specialized execution strategies. We've seen this in the case of negation, where we've introduced stratified evaluation to solve our problems. And similarly for equality and disequality of terms, and also for arithmetic relations. To support their intended meaning, we may need to delay the execution of a goal until more becomes known about the arguments. And therefore, supporting built-ins may restrict the admissible execution strategies. We can no longer run goals in any order, but may be forced to use a particular order or delay goals until more is known. So that's the price we may have to pay to support these extensions. Just as for Prolog, that's the same for Prolog. And note especially the direction of causality. The built-ins may necessitate adaptations in the execution strategies, right? The built-ins have this effect. It's specifically not we need special built-ins because of the execution strategy. That's also a misconception I sometimes see about Prolog. People saying, well, Prolog has a particular execution strategy and therefore we need so many impure constructs. That's a fallacy and confusing cause and effect. The direction is, if we use constructs that only work under a particular execution strategy, then we are stuck with a specific strategy. Pure Prolog does not enforce a fixed execution strategy. It has a default strategy, yes, and we can also run it with other strategies, as we've seen, for example, with tabling. So we forget this. And for many programs, we can statically detect which built-ins are actually used. So we could restrict this from supported to those that are actually used. Because the fact that a built-in is available does not mean that we have to use it. And by wisely choosing the built-ins we use, we can enlarge the set of applicable execution strategies. And a very useful class of built-ins are the pure monotonic built-ins, because they can be used with any execution strategy, and they also allow declarative reasoning about programs, because if too little is known, then they yield instantiation errors or delay the execution. So they never give wrong answers, no matter which strategy we use. And that's nice, because we want to be able to try everything we can to deduce consequences. Some strategies may work better than others for a given task. So for implementers, an important question is, which built-ins should be added to Datalog? Because they increase the expressive power of the language, and on the other hand, they also increase its complexity. In fact, the complexity can become so great that the logical consequences are even no longer decidable. For instance, consider arithmetic constraints over integers. Linear constraints over integers are decidable. They are NP-complete, so presumably of lower complexity than Datalog. But if we add linear constraints or even only successor to Datalog, then it's no longer decidable over integers, only semi-decidable. And likewise for rational, real and complex numbers, even though linear constraints over them can even be solved in polynomial time. That's because recursion plus successor can express addition and multiplication of variables, and so we can use it to express arbitrary computations by Matijasevich's theorem. And some extensions of Datalog can't be expressed as built-in predicates, but require syntactic generalizations. For instance, disjunctive Datalog, where we allow disjunctions in clause heads, or existential Datalog, where we allow existential quantification in clause heads. So we drop the safety condition we mentioned earlier, and so on. But at least ideally, the resulting programs are still valid Prolog terms. Maybe not valid Prolog programs, but valid terms. Because this means that we can easily read and analyze them and also interpret them with Prolog. And common consequences of all extensions are, as already mentioned, multiple minimal models, as for negation and disjunctive Datalog, more expressive power, that's the motivation for extensions, and higher computational complexity, even up to undecidability, as in the case for existential Datalog, or Datalog with integer constraints or compound terms. And undecidability may sound bad, but at least in my opinion, it's often not as bad as it may sound. Because many things are not decidable, only semi-decidable, such as compilation of C++ programs, which is Turing-complete, or LaTeX, which is also Turing-complete, PostScript, and so on. All these mechanisms are not decidable and may not terminate, and in practice that's no problem at all. We still use C++, LaTeX, PostScript, and so on. Because what's the main drawback of this? Is it that running such applications may cost CPU time? That's okay. We can run them for as long as we can afford and then stop. So, in conclusion, Datalog is a quite interesting and attractive language, and it strikes a very interesting balance. It has a very simple and uniform syntax, it's quite expressive, it allows declarative debugging, as in Prolog. It's found at the intersection of logic database theory, complexity theory, and other domains, such as universal algebra, and this makes it very interesting from several different perspectives, and it admits powerful and seamless extensions which make it even more expressive. And for us as Prolog programmers, it's also interesting because every Prolog programmer must master at least the functor-free pure subset. So Datalog must be mastered by all Prolog programmers. And every attraction of Datalog holds for this subset of Prolog. Datalog vendors should keep this in mind, especially for marketing purposes, because how do you want to market a Datalog system? Be careful when contrasting it with Prolog, because it's a proper subset of Prolog. So any advantage you mention for this subset also holds for all Prolog programs in that subset. But you can of course advertise your custom extensions, or for example take an advantage of Prolog and also use it for marketing your Datalog system. And I mention this because the intensity of conflicts often increases with conceptual proximity. For instance, Java and C++ programmers may not even have heard of Prolog, because they are conceptually far removed. In contrast, Lisp programmers often have at least a vague impression of Prolog, because several Lisp books mention Prolog and show how Prolog's default execution strategy can be simulated with Lisp macros. With Datalog, we come even closer to Prolog, and now the intensity of conflicts increases. Datalog vendors correctly regard Prolog systems as competitors, and thus may be tempted to downplay the importance of Prolog or overstate advantages of Datalog in comparison to Prolog. And all of this pales in comparison to the conflicts between different Prolog systems. At least in the past, there were fierce flame wars between Prolog vendors. And in a sense, this is natural, because it mirrors what we see in nature. Some of the fiercest conflicts arise between people that are most closely related. And maybe the fiercest conflicts of all arise within individuals. Now, how do we bring Prolog into the world? Ideally not by engaging in fierce conflicts, right? But Datalog may be a good start, because many business cases need transitive closure. It arises, for example, in cost accounting, where we describe the structure of costs. Many businesses need to model such relations, and Datalog makes describing and querying them easy. So in due time, large database vendors such as SAP and Oracle may become interested in Datalog to store this information. And by then, we must have everything ready. For example, the Prolog ISO standard already lays a solid syntactic foundation and also improves over time. And such use cases for businesses are also a very good reason to keep to the standard Prolog syntax in Datalog systems, because it makes your solutions more readily usable in highly regulated areas, such as governments. And functionality that goes beyond the standard can be added to Prolog systems with conforming extensions. A Prolog system can provide extensions that are especially useful for Datalog, but they should be conforming extensions, not modifications. This means that valid Prolog code must still be handled correctly. And this could be a good way to bring Prolog into the world. Start by providing Datalog solutions to businesses and retain a path towards full Prolog. And one way to do this is to start with a Prolog system and to use only its Datalog subset. And there are countless potential applications for this. For instance, take the Data Governance Act. This is an existing law of the European Union, and it has quite far-reaching implications. It regulates conditions for the reuse of data, provision of data intermediation services, registration of entities, and so on. And for example, in Article 8, we find important obligations for member states, such as they must ensure that all relevant information is easily accessible through a single information point. And that single information point must be able to receive inquiries, provide a searchable asset list, and so on. So quite complex data governance tasks. And the good news is that member states still have a few weeks left to do all this. And it's directly applicable in all member states, so a huge business opportunity. And how will governments implement this? Well, most of them will have heard about relational databases, which can be used to store and query data. And at first glance, this may seem like a good solution. Just set up relational databases and store the data there. But a common consequence of such architectures is that they end up with the database as silo. It's often even drawn as a silo in presentations. So this means that we have the database, and invariably we need additional formalisms to express application logic, because the database only contains the data and can't really reason about it. And that's unfortunate, because data governance is getting increasingly complex, and the demands on it also rise all the time. Because when making data available, we also need to think about data protection, access rights, and so on. And therefore, we need better technology to store and reason about data. Because at least I think it's pretty obvious that the current methods don't work well. We currently have far too many problems with data management. The databases are too low level and too hard to use. And a key attraction of Datalog is that it lets us describe relations in terms of relations. And that's great, because we can quite easily use available building blocks to formulate new concepts and use them for reasoning. And also we can easily extend Datalog to incorporate, for example, results we obtain from other databases via network connections and so on. This can be seamlessly embedded in Datalog with new built-in predicates. And a major promise is, of course, that the same formalism can be used to store data and logic. And on top of it, the formalism is also very simple, because if you think about it, Datalog only provides a single language element, namely horn clauses. And with only this one language element, we can store data as facts, use rules to describe logical consequences of the data, and also formulate queries. And if you're interested in such topics, then Datalog and also Prolog may be well worth a look.